Thank you all so much for coming to see my talk. I really appreciate you showing up and being interested, and thanks for any Strange Loop organizers who may be in the room for hosting the talk. It's a real pleasure to be able to come here. I've been wanting to come to Strange Loop for a long time. At this talk today, I'd like to give you just a little taste of what dependent types may have to offer. I'm not going to teach you sort of the deep mathematical background or go into how you can use them at work, but I hope to at least convey just a little piece of the joy and beauty that I think dependent types have. My name's David. I work in sunny Portland, Oregon at a company called Galois. But for the last couple of years, I lived in Bloomington, Indiana, where I was a postdoc at Indiana University, and Dan Friedman, my co-author, who's sitting there in the third row, and I put this book together through a couple of years of hard work, so I hope you like it. So, what are dependent types? Why might you think they're kind of fun? Well, maybe you've been reading a blog post about how fun it is to write code in Idris, which is a dependently typed language that looks a lot like Haskell, except it uses 1 colon to put a type on a thing, and 2 colons to make a list. Or you may have been working with Agda, which is Idris's older cousin, which is really a wonderful system to work with. Or you may have looked on as people end up making an entire C compiler and proving that it doesn't have any bugs at all using a system called Coq, which has also been used for tons of other really large-scale, impressive projects. The fact that the French government has funded the development of Coq for such a long time is a wonderful gift to humanity, and we should all be grateful to them. Or you may have been looking at big mainstream languages like Scala and Haskell, and and seeing that more and more patterns that people are using on a daily basis are inspired by dependently typed programming, and thinking, well, what are these dependent types? But like most great things in computer science, dependent type theory didn't start in the 90s, long ago in the 90s. It didn't start in the 2000s. It started around the last turn of the century, not the most recent one, when I was in high school, but the one before my birth. And there was a controversy in the philosophy of mathematics saying, like, well, what are we doing when we do mathematics? And the traditional account, going back to the ancient Greeks, to Plato, has been that the world is some sort of poor reflection of the true existing objects of mathematical reality. You know, the circle on the top of my coffee cup is sort of like a bad version of the ultimate circle. And people started thinking, well, there's some problems with this approach. And the official thing that we have, which was sort of famously advocated by David Hilbert back then, was this idea that mathematics is actually ultimately meaningless. We're not accessing the true high reality of things. In fact, we're just playing games, meaningless games. And we're playing those meaningless games with meaningless symbols according to arbitrary rules. And it just so happens that we like some of those arbitrary rules better than others. And eventually, hopefully, we'll have machines that can play those games better than we can. Another approach that was pioneered by a Dutch mathematician, Brouwer, who is not as well known as David Hilbert, but has done a lot of wonderful things, is this idea that actually mathematical objects aren't meaningless, but they also don't sort of exist prior to and above and beyond the world that we actually live in and inhabit on a daily basis. Instead, they exist in the minds of people doing mathematics. They're fundamentally about ideas, about our own experience of these mental constructions. And sort of coming out of that philosophical tradition, as well as some later European philosophical traditions, the Swedish philosopher Per Martinlöv put together his intuitionistic type theory starting in the 1970s, also prior to my own birth. And intuitionistic type theory took some of what Brouwer's students had done, putting intuitionistic logic, Brouwer's theory's intuitionism is what it was called, and taking a sort of a form of logical reasoning that was appropriate for this idea of mental constructions, and building it up so that it was a much bigger theory, sort of big enough that we could do all the math that we want. And Per Martinlöv put out a few different versions of his intuitionistic type theory. And meanwhile, Thierry Cocon and Huet, they were working on the calculus of constructions, which was another approach to doing this. And it turns out that Martin-Live's type theory and the calculus of constructions look an awful lot like functional programming languages. And then, meanwhile, in the British Isles, Zhao Luo put together a core type theory that was sort of a version of the calculus of constructions with inductive types and a lot of extensions used in the Lego system. And then the calculus of constructions itself, as being developed for the Coq system, which we mentioned earlier, that inherited a lot of the features that were eventually developed in the Swedish context, and we ended up with a lot of convergent evolution of these languages, ending up with the actual systems that you could sit down and use and type things in. So we have Coq still today. An early alternative approach was epigram, and epigram inspired a system, Agda, which was based on earlier Swedish systems. And Idris was inspired by epigram and Agda. A lot of previous epigram people worked on Idris. And today we have these things in languages that we can download and run and reasonably use to write real programs. You can write Pac-Man in them, as Idris's creator, Edwin Brady, likes to say, that Pac-Man completeness is more important than Turing completeness. But it's one thing to be able to use something on your computer. It's something else to get insight into the inner workings of it, to see how it works. And that knowledge has been pretty hard to acquire traditionally. You have to pretty much know somebody who's able to point you to the right papers and help you interpret them and say, oh, that thing they're talking about there, where do we go for the information to understand the context and the ideas, and sort of build up the intuitive understanding that allows you to read computer science papers as interesting literature rather than as a chore that you have to struggle through. And that just takes a lot of time. And so a mutual friend, Adam Fulzer, introduced Dan and I and said, well, hey, Dan's writing these series of books like The Little Schemer that teach deep ideas without assuming that you're a mathematician. Maybe the two of you could work together on one for dependent types. And we said, yep, that sounds great. And we just finished it. It came out last week. It's called The Little Typer. Oh, thanks. And the response has been a little overwhelming, and I'm very happy about that. Thank you. And so for the Little Typer, we didn't feel that we could use an existing dependently typed programming language because it turns out that in order to make these things practical for getting real work done, you automate away a lot of the things that are difficult to do. But sometimes confronting difficulty and overcoming it is an educational experience. It teaches you how to work with a thing. So we wanted to put together a language that we could use to demonstrate the fundamental principles of dependent type theory without anything being automated away, but where we could still fit it in the narrow two-column format of a little book. And we didn't find one that suited our needs, so we made our own, and it's called Pi. So I'd like to give you a little demonstration of how Pi works. And this is PIE, the kind you eat. So I'm going to write a program in Pi, and that program is 5. I like the number 5. So looking at the screen here, we can see that I typed 5 up top, and Pi responded saying, that's the nat 5. And it's also got a little green check mark down in the corner, which means your program is A-OK. I could also write 23, and it responds 23. Programs that evaluate to themselves are not the most fun of programs. We'll get to some more functional programs later. But in the meantime, let's look at a few more simple programs. Sometimes I want to do things other than numbers. I like food. So one kind of food that I like is apples. So I can type apples with a quote mark. And Pi responds, apples. Yep. But note that it's also got another thing after the word the. So before we had the nat 5, but now we have the atom apples. So the thing between the and the result of the program is what we call a type. And a type describes a program. It tells you a lot about what that program is going to do. And in the case of nat, it means it's going to give you back a natural number. So some of the natural numbers are things like 0, add 1 of 0, add 1 of 0, and so forth. Negative numbers are unnatural. We can also write the descriptions ourselves. So I can say the nat 23. I can say the atom pizza. I can even say the atom wupol, because I like wupol. It's very delicious bread. If you ever go to Denmark, get some. But I have other descriptions than just nat and atom. There's some descriptions that combine other descriptions. So I can say the pair nat atom, and we make pairs with our good old friend cons. So we can say cons 23, and I didn't come up with a list of food. What's your favorite food? Somebody tell me. Ice cream. Ice bread, what? That's not food. so then we get back the pair nat atom, cons 23 ice cream. Pretty tasty. 23 ice creams. Might get a stomachache, actually. How about we just say 2 ice creams? That's suitably decadent. But if I were to say cons ice cream 2, then I get back, instead of my friendly green check mark, I get an angry red X. And I find out that pi expected, based on the description that I gave it, a nat, but instead I gave it an atom. This is the dreaded type error. And for a very fun program, I can write a function. So I can say the arrow nat, and then we use our old friend lambda, and let's say we just want to turn the same nat. And then we find out that lambda k is a function where when we give it a nat, it'll give us back a nat. That's what this arrow means. A lot of languages put the arrow in the middle, but I like it at the beginning. I can also write lambda k plus k. And I can write lambda n and plus n. I can even use the letter j if I want. It turns out that changing the name of a bound variable doesn't affect the meaning of a program, thankfully. So that's pretty cool. Types tell us a lot about our programs. Throughout this, I'm going to be showing some of the chapter art, both to demonstrate to you that we're flying through this book, and also because I really love the artwork that Dwayne Bibby made for our book. I'm super happy about it. Here we see the elephant from The Little Schemer handing a basket of parentheses to this bear who's about to learn type theory. So not only do types describe programs, types also tell us which of the programs they describe are the same as each other. And it turns out that 4 is the same nat as 4. And here I'm asking pi, would you please check for me that 4 is in fact the same nat as 4? And it replies with the green check mark. Indeed, 4 is the same nat as 4. If I were to ask whether 4 is the same nat as 5, well, it's not. 4 and 5 are not the same nat. But sameness is not entirely trivial. For instance, I can also say, check whether 2 plus 2 and 4 are the same nat, and I can check whether 1 plus 3 and 4 are the same nat. And indeed they are. This means that sameness respects computation. That's sort of one of the key insights that Per Martinlöv had, was giving us a framework in which we could make a language that automatically respects computation. And this works for all the types, not just the types like nat and pair, where you can imagine behind the scenes there's sort of a layout in memory that can be checked of values and having bit-for-bit identity or some sort of recursive function that traverses them and checks them. In fact, we can check whether 2 functions are the same. So we can see, for example, that lambda k is the same arrow nat as lambda j. So these don't compile to the same thing, or maybe they do, depends on the compiler, but sameness is about the meaning of the program much more than it's about the eventual result of compiling it and checking some values in memory. And what we can even see here is that, let's say we add 0 here to k. So it turns out that lambda k plus 0k and lambda j are the same function from nat to nat. I could also say plus 1 here, they're not the same, and add 1 here, and once I balance my parentheses, they're the same again. So sameness respects computation even inside of a lambda. That's pretty neat, I think. So, so I've shown you a lot of ways to build things up, but not a lot of ways to use the things that have been built. So we're not only interested in programs that put together a number or make a function, we're also interested in programs that do recursion over a number to do different things depending on which number we got, and we're interested in programs that apply functions, that call them to find out what their value is when provided with an argument. We call this eliminating those things. It sounds very stressful, actually, like I'm going to eliminate those functions, but it can be friendly. And here we see some natural numbers being eliminated from this bear's cave. So I've been acting so far as though plus is something that we completely understand, but plus isn't a built-in in Pi. We have to build it ourselves using simpler tools. So when I say claim, that means I'm about to define a thing called plus, and it's going to be described by the type arrow nat nat nat, which is to say we're going to give it 2 nats, and it'll give us back a nat. So having claimed plus, I'd better define it. Note that Pi is not entirely convinced yet. It's got this, this question mark down here. I don't know. That plus looks suspicious. We'd better define it. So we define plus, and well, how are we going to define plus? Well, Pi looks kind of like scheme. It's not scheme, but it looks kind of like scheme. So let's try writing it in scheme. So we could say, well, the first thing we'll do is we'll check whether, we're going to say lambda first. Lambda jk. And then we're going to check, well, is j 0? And if j is indeed 0, then we're going to return k, because 0 plus k is k. And if j is something other than 0, then our answer is going to be the result of adding 1 to the result of adding 1 minus j, so j minus 1, we write sub 1 of j, to k. But we've got a problem. Pi doesn't have if. Pi doesn't even have booleans. It turns out that you can build booleans out of simpler tools. So what are we going to do here? Well, each type, not only does it come with constructors, which allow you to build the values of those types. You've seen some constructors already, like 0 and add 1, like lambda, like every atom is a constructor. But we also have these eliminators that let us use things made out of that type to make things in any old type. So here we can use an eliminator called which nat. Because that's what we're doing, right? We're checking which nat we've got. Have we got 0, or have we got add 1 of something else? And if we've got 0, well, we're going to check that on j. And if we've got 0, we want to return k, just as before. The second argument to which nat should be a function. So I'm going to control k here and say lambda. And this function, if we've got if j is add 1 of something, then that something is the result of j minus 1. So I'm just going to call this variable j minus 1. We're allowed to have hyphens in variable names here. And then the result will be add 1 of plus j minus 1 k. And we're almost there. Except we're not. Oh no. So what we've tried to do is we've tried to define plus using plus. But it turns out that in Pi, when you're defining things, recursion is just not an option. Hey Dan, why is recursion not an option in Pi?
Because recursion is not an option.
Yeah, but why isn't it an option?
Recursion is not an option.
But why isn't recursion an option?
Recursion is not an option.
So it turns out that when you want to use your programming language as a logic, as a source of truth, then justifying things by themselves is a little bit problematic. And indeed, recursion is not an option in Pi. So instead, we rather than defining things recursively where they refer to themselves in their own right-hand side, in their own meaning, instead, each type that has a recursive structure, like the natural numbers, provides an eliminator that exposes the structure of those values in such a way that you always make progress down to the base one. So we have an eliminator now called recnat. Recnat is very much like whichnat, except that this function here takes one more argument, which is the result of the recursion on j minus 1. So here we're going to call that sum so far. And now the sum so far is plus j minus 1 in k. So I can say sum so far, and I get that green check mark. And just to see that it works, because even if you're going to prove something is right, you should probably test that it's right first to save yourself hours of pain. We want to say plus 3, 5, and we get the nat 8 back. So this thing works. And because we didn't use j-1 ever, I can just go ahead and get rid of that and then use a slightly simpler eliminator called iternat, which simply doesn't pass the one smaller nat. And now we have the definition of plus from our book. We've read a few chapters now. Another thing I might want to do is to double a number. So let's walk through that process one more time. So I can say define double, and then it'll be lambda n, we'll call it this time, for no apparent reason, and say rec nat n. And what is double of 0? 0, I hear it from the audience. Great. So double of 0 is 0. And how do we double a number that is 1 smaller than n? We'll call it lambda n minus 1 and so far. Well, we put 2 1s on top of it. So we can say plus 2 so far. And then we get back double. So we can say double of 3, and we get back that it's the nat 6, just as expected. So types so far have been describing things that are like the programs we know and love from most of our other programming languages, but it turns out that types can describe much more than just numbers and atoms and pairs and functions. Types can also describe evidence, which is to say evidence for some statement. In this case, we're having the claim that 2 plus 2 is 4. I hope you agree. If you don't, I'm going to prove it to you. So, evidence that 2 plus 2 is 4, well, let's think. 2 plus 2 and 4, those are the same nat. We saw that earlier. So we can see, define 2 plus 2 is 4. I should get autocomplete in my slides. And that's going to be same 4. And what we're saying is that 2 plus 2 is equal to 4 because 2 plus 2 is the same as 4, and 4 is the same as 4. I could also give evidence that they're equal by saying plus 1, 3 here. And now I'm saying that the evidence that 2 plus 2 equals 4 is the fact that 2 plus 2 is the same as 1 plus 3, and the fact that 4 is the same as 1 plus 3. I could even write plus 3, 1 here, and it still works. So that's one kind of statement, that things are equal. But actually, we have lots of ways of making statements, and we have ways of putting other statements together from smaller statements. And so we should think, what is the evidence of those? And it turns out that the evidence of those things is already things we've seen. So if we have two statements, A and B, and we want evidence for the combined statement A and B, well, that's a pair. And the car is evidence for A, and the cooter is evidence for B. Or for those who are used to other languages, the first thing in the pair is evidence for A, and the second thing in the pair is evidence for B. And A or B, well, there's two ways that we could have evidence for A or B. We could have evidence for A, or we could have evidence for B. And pi includes a type called either, which captures this situation. What about evidence that A implies B? So what I want to know is that whenever A is the case, B will also be the case. And the way I can capture that is to actually write a function. And this function should be able to take any old arbitrary evidence for A. You know, like maybe there's multiple ways to get evidence for A. For example, maybe A is an or, so it could be a left of one thing or right of another thing. But whatever it is, we should be able to take any evidence for A, and given that, produce new evidence for B. That's a function. That's a program. And then, as we've seen, if we want to see that x and y are equal according to the type A, well, when they're the same A, then we get to use that constructor same that we saw before. What about a false statement? What counts as evidence for a false statement? Nothing whatsoever. If we had evidence for a false statement, we'd be in trouble. Another way we can make statements is by talking about particular programs or particular values, particular individuals. So what this type sigma says is that there exists some atom, and we're going to call it fruit, and it satisfies a property, namely that whatever fruit it was, it's equal to orange. So I can say, it turns out that sigma is actually a fancier version of pear. So I can say define orange exists, and then it's going to be cons, and I want to pick some fruit, apple, because I like apples, and then we will say same apple, because we want to show that it's equal. And it turns out that it's actually not equal to orange. What happened was, the first thing in the pear, the car, that's apple, but the second thing here, it was supposed to have the type that whatever fruit, in other words apple is, that it's equal to orange, but apples aren't oranges. So instead, we should say cons orange and same orange. And then we get our green check mark. In other words, sigma is the type of what we call dependent pairs. The type of the second thing in the pair is allowed to refer to the value that is the first thing in the pair by name. And actually, pair, the type we saw earlier, is an abbreviation for sigma where that name just isn't used. So if we want to define what it means for a natural number to be even, then we get to write a function, because we want to work for any old natural number. So even is going to be a function that takes a nat and then gives us back something called a u. U is a type that describes many other types. It doesn't describe itself, because that would make various things go wrong in the logic. But it does describe types like atom and pair atom nat and functions, and also sigmas. And so even is going to be something where we give it a nat, and it gives us back the type that describes evidence for that particular nat that we just gave it to be even. So, it's got a lambda. And note that I wrote to do here. So in Pi, sometimes it's nice to not have to write a whole program at once, so we can sprinkle it with to-dos and get back to them later. And we'll just have that little yellow question mark until we're ready. So what does it mean for a number to be even? Well, it means that we can cut it in half evenly. So in other words, it means that there exists some other number, so sigma, and we're going to call that other number half, and it's going to be a nat. And what property does that number have? Well, it turns out equal nat, n, and then double half. Because if you double half of something, you should get it back. And if n were an odd number, then we wouldn't be able to do that. We wouldn't be able to cut it into something where doubling it would get it back. So if I want to see what is even of 6, then we see it's this u, this element of the universe, which is what u is an abbreviation for, sigma half in nat, such that nat equals to, and then we see the definition that we ended up writing for double getting unfolded a little bit here. Yeah. So this is now we're on chapter 12, by the way. The book proceeds at a pace which I think help you keep up with it. Is 0 an even number? Well, I've heard some controversy on that fact, but given the way we've defined evenness, it is. We can prove it. So we need to find evidence that 0 is even. Because even 0, well, if we think about what does even mean, well, that means sigma half. So we got to figure out what half of 0 is. And half of 0 is a number where doubling it gives you back 0. Yeah, it's 0. Good job. Awesome. So it's going to be cons 0, and then same 0 is the evidence that double 0 equals 0. Because double 0 is the same nat as 0, so it all works out. So 0 is indeed even. We've solved the mystery. And if we want to get evidence of oddness, well, that's going to be, let's see. So when we cut it in half, there's 1 left over. So we'll say sigma half nat equal nat n. And now we want to say add 1 of double half. But wait, half is the wrong name. This isn't half. It's almost half. So we're going to call it half. And so evidence of oddness says that we've got this half, which is almost half. In my dialect of English, we pronounce them the same, which is kind of unfortunate. But yeah, and so if we wanted evidence that 1 is odd, we could say the odd one, cons 0, same 1. And it works out. And now we're to chapter 13. So one thing I might want to do is I might want to talk not only about a thing that exists that has some property, but we may also want to say that everything has some property. In other words, we talked about there exists, and now we want to talk about for all. And just as there exists ended up being a version of pair with more information, for all ends up being a version of arrow with more information. So we can say pi n in nat. That is a type that describes functions that are going to take an argument which is a nat. But then we're going to name that argument, and then we can use the argument itself in the rest of the type. So what this type describes is functions where we give them some nat that we call n, and then we give them furthermore evidence that whatever n it was we gave it is even, and it'll give us back evidence that add 1 of that n is odd. And so I've written part of this already. Note that this lambda looks like it takes 2 arguments. That's because pi curries all of its functions just like Haskell. In other words, if I write what looks like a function with 2 arguments, it's actually 2 nested functions, each of which take 1 argument. Every function in pi actually takes 1 argument. And so I've got n, and I've got evidence that n is even, and I need to make evidence that n plus 1 is odd. So if n is even, well, let's see. So 0 was even, half of 0 was 0, and 1 was odd, and almost half of 1 was still 0. So when we go up a number from an even to an odd, then the half of the even number is almost half of the odd number. So we can take the car, which is to say the first thing, the half of the even number, from the evidence that n is even. And then the evidence that doubling that and then adding 1 is equal to our current add 1 of n. Well, we get that by, well, we know that doubling car of n is even gives us n, and so we just need to add 1 to both sides of that equation. And doing something to both sides of an equation should certainly be okay, because if 2 things are the same, then nothing can distinguish between them. So we can use an operator called Kong. And so Kong, we say, coulter n is e. And what are we going to do to both sides of the equation? Add 1. And this works out. So now we've proven that 1 greater than any even number is an odd number. And you can do the same thing to prove that 1 greater than an odd number is even. I don't want to bore you. Oh. So now this leads us to be able to pose a question. Is every number either even or odd? Well, I claim that it is. And the way we're going to do that, the way we're going to figure that out, and this either, by the way, is the type that we talked about earlier for evidence of an or, using a version of recnat called indnat, which allows the recursion to talk about the actual value being recurred upon right now. In other words, we have 1 more argument, which is this first to-do, and we get to use this to-do to explain the relationship between the n we're looking at and the type of the entire recursion. In this case, it's lambda k, either even k, odd k. And now our to-dos say, well, in this case, right, this is the base case of our recursion, so when n is 0, then we need either evidence that 0 is even or evidence that 0 is odd. And we know how to do that with left, which lets us take the left side of an either, and it's going to be 0 is even, which we already found earlier. And for the case of the step function, the thing that takes the result of the recursion on n and gives us back the recursion on add 1 of n, well, for that we're going to write a helper. So this helper here is called step of even or odd, and it takes some n minus 1, some almost the n we're looking at, and evidence as to whether n is even, n minus 1 is even, or n minus 1 is odd, and gives us back evidence that add 1 of n minus 1 is even, or that add 1 of n minus 1 is odd. And so if we want to write that function, for that we use something called int either. So we're going to take our n minus 1, we're going to take evidence that n minus 1 is either even or odd, then we're going to take that and produce evidence that, well, either 1 greater is even or 1 greater is odd. And the way we do that is by cases. If it were left, then we know that n minus 1 is even. And we know that if n minus 1 is even, then add 1 of n minus 1 is odd. So we put the right constructor around it, and then use this add 1 even odd in order to transform the evidence that n minus 1 was even into evidence that add 1 of n minus 1 is odd. Likewise, if n minus 1 was odd, then we know that add 1 of n minus 1 will be even. So we can use this helper, add 1 odd even, to transform evidence that n minus 1 was odd into evidence that add 1 of n minus 1 now is even. And putting all the pieces together, we have our green check mark. We've proven that every number is either even or odd. Well, we've done a little more than just proving that every number is even or odd, right? We were walking through this thinking, okay, so what does it mean, like, for all there exists, or, and, talking about our program in sort of logical language. But that's not where we started out. Way back at the beginning of this talk, I was talking about pi as a programming language. And it turns out that we've just written a program. So I can say even or odd of 0, and scrolling past the definition of what it means for things to be even and odd, we see left, and then that very evidence we wrote earlier. So we got a program where we give it 0, and it gives us back evidence. First off, it gives us back the fact that that 0 is even, and evidence of that evenness, namely half of 0. If I say even or odd of 100, then we get back that, well, yeah, it's even, and half of it is 50. What if I say 113? Well, then we find out that right, it's odd, and almost half of 113 is 56. In other words, the proof that every number is even or odd is something that determines the parity and figures out how to cut it in half. I think that's pretty neat. I love this stuff. So thank you so much for coming to this talk and for listening. I really appreciate it. If you want to read the book, if you have any questions, you can get a hold of Dan or I. I have Twitter. We both have email. And if you're interested in learning more about type theory, the little typer's out, and it would be great if you wanted to read it. Libraries are wonderful. You don't have to buy it. Thanks so much.